Hi there, my name is Ron Rogers, and this presentation deals with the crash of Air France Flight 447. This was a flight from Rio de Janeiro, Brazil to Paris, France, and the crash occurred on 1 June 2009. Now, this was a totally preventable crash, and I think most private pilots with less than 100 hours understand the concept of pitch and power, and they could have kept this aircraft out of trouble. And part of the issue here is just a lack of basic flying skills. This crash occurred 3 hours and 6 minutes after takeoff. The crew consisted of two co-pilots and a captain. The captain took what's known as the first break. So shortly after takeoff, he went back into the bunk, and the two co-pilots are up in the seats flying the aircraft. Now, when I was chairman of the ALPA National New Aircraft Evaluation Certification Committee, we went over and we flew all the Airbus aircraft, and we would get these marketing brochures is probably the best way to describe them. They're not really technical brochures in the fact that they don't lay out all the specifics of the flight control, but they're kind of they put a marketing slant on it. And they talk about, yeah, you're just not going to lose pitch control. You're not going to lose the elevators. You know, the flight control computers do wonderful things. They're designed, you've got primary flight control computers, you've got secondary flight control computers, and they do all sorts of wonderful things for you. You've got all sorts of high angle attack protection, pitch protection, bank angle protection. Interesting thing about this, of course, there is no direct stick to elevator control, and the throttles are not directly to the engines, and they don't move. Moving auto throttles is another thing that I think is kind of nice to have, to see the thrust. With the setup in the Airbus, you can have the throttles at idle and go into alpha floor and have full power on the engine while the throttles are back at idle. You can have the throttles in the full, what would be full forward, and be at idle power because that's what the computer is commanding. Gets interesting, doesn't it? So we talk about the normal law, which is where you usually are, and it does various things for you. It makes the airplane fly better. It enhances flight control. It prevents you from getting in trouble. And this is what Airbus was touting early on, was pilots just can't crash this airplane. We're building an uncrashable airplane. Of course, that's gone by the wayside so long ago. I think most people don't even remember what I would call their extreme excessive arrogance on claiming they had built an uncrashable airplane. And that was told to me directly by test pilots in the program. So we got the normal laws, we got the protections. Here we have kind of a very extremely basic block diagram, and like it says, there's no direct relationship between side stick and control surface deflection. And then we got the pitch controls. We got trim that goes back there mechanically. That's if you're in direct law. And you've got the autopilot, the stick there. The autopilot can command various actions. You have three primary flight computers, two secondary ones, and a little switch there going from normal to alternate law. And alternate law is the big bugahoo we're going to talk about. All right, so normal law is where you normally are and everything's fine, everybody's happy. Getting to alternate law, you need a couple of failures. Well, that's kind of interesting. You know, you don't usually get a lot of failures. But if things do go wrong, the primary flight display kind of shows you. Instead of those little dashes up there in normal law, you can go to alternate law and you get the little X's. And based on experience, I'll tell you, those X's don't always get your attention. Now, when you go to direct law and you get the use manual pitch trim, it doesn't say you're in direct law. It says use manual pitch trim because you have no trim in direct law. So, okay, we're in alternate law. Yeah, that's just not going to happen. Everything pretty much works nicely, and protections, well, we lost pitch attitude, we lost the high speed, high angle of attack, well, we got static stability. Okay, that's what normal airplanes typically have. And direct law, it's pretty much manual. Now, the interesting thing in this marketing brochure is they didn't mention a very important fact. And there's the red arrow. In alternate law, the airplane can be stalled. And actually, that's how we typically did stalls. And the funny thing was, when I went to Airbus captain training. They said, "Well, how do you get into alternate law?" And I said, "Well, what I usually do is I ask Fernando, the flight test engineer, to put us into alternate law or direct law, which is how we did on the flight test aircraft. He's back there in the flight test station, and he can do it." But up there in the green arrow, you can see you got all sorts of combinations of these laws, depending on what may be going well and what may not be going well, and it can be very confusing. Yeah. So it was a dark and stormy night over the Atlantic there, and they're heading on, and they were getting into icing conditions. Now, pitot tubes are heated, and they're supposed to take care of this, but they were getting they were having some problem with these pitot tubes, and they went through several iterations of design, and they were doing a lot of replacements, and that little history gets kind of complicated. But basically, the pitot tubes were having a problem on the Airbus aircraft, and of course, pitot tube is your airspeed sensor. Now you got several things that kind of help you out on airspeed. You got three systems. You got a left, a right, and a standby. And apparently they were getting enough icing that it took out enough of these systems, maybe even all three, because they were getting very erroneous airspeed indications. But you still have the angle of attack indicator, and that should really help you out, right? The flight test Airbus aircraft I flew had a nice little angle of attack indicator down on the left instrument panel there, so you could sit there and you could look at your angle of attack. Well, that was kind of an extra, and I never saw it outside of the flight test. My airline decided we're not paying for that. So the pilots had no direct indication of angle attack, and these pilots also had no direct indication of angle attack. And one thing's interesting, this was a very new Airbus A330 that Air France had. In fact, it was the newest at that time A330 that they owned. Now these are the pitot tubes I'm talking about. You can see the placement. You got the captain's on the left there, and on the right side you've got the right pitot tube and also the standby tube. And above those in the red circle, those are the AOA sensors. Now, shortly before the crash, approximately 4 minutes or so, they got into the airspeed indication problems. And the nice thing about the Airbus flight control system, it goes, we don't like this. We've got indications that don't make a lot of sense. So the autopilot disengages, the auto thrust disengages, and the airplane basically says, "You've got it." Well, this startled the two co-pilots that were up there. It also puts it into alternate law. They take you out of direct law because the airplane kind of doesn't know what's going on. And what happened was the pilot on the right side, who was designated as the pilot flying, grabbed the controls. And one interesting thing about the control laws is you're limited. The stick in roll commands 15 degrees per minute roll rate. Now, when you go into alternate law, the airplane has a natural roll rate of 20 degrees per second, and it's a very sharp, I've flown this in flight test, it's a very sharp leading into the roll. You start it, and it's very crisp. It's almost like it's not a 104, but it's almost like an F-104 that has a very crisp initial roll rate. And it can be a little bit unnerving because you just barely move the stick, and the thing really goes on you. In fact, they used to have the roll rate at 20 degrees per second, and they've got into some pretty bad pilot-induced oscillations in the flare in roll on this, and when they reduced it to 15 degrees per second, maximum roll rate, that went away. So that was kind of the solution there. But and you should practice this in the simulator, but it's probably mostly initial stuff, and the guys don't really get to see it. But the airplane gets rather twitchy in roll, and they speculate that this may have kind of startled the first officer who was flying, and he inadvertently abruptly applied full back stick. Well, the airplane was at 35,000 feet cruising, and it suddenly goes up to 38,000 feet, and the stall warning briefly sounded, but he exceeded the tolerance of the angle of attack. Now, this I find interesting. They dropped from 274 knots to 52 knots. Now, it's very unusual to lose airspeed indications in a transport aircraft, especially when you got three systems. I've lost airspeed in the military and in civilian. I landed a T-38 indicating 500 knots, but we had a nice AOA indicator, so I could fly it back using that. And but in this case, they lost the airspeed. It confused the flight control computers, and it confused them also, the pilots flying also. And the aircraft, as I said, climbed. The angle of attack increased to 16 degrees. The thrust levers were in the full forward position. They were commanding full thrust. But the aircraft began to descend, and the angle of attack rapidly increased towards 30 degrees. Okay, we're in a full stall here. And this was roughly 3 minutes and 30 seconds before water impact. They impacted the water in a full stall. As the aircraft began to descend, normally the stall protection would have operated in direct law, but since they're an alternate law, they didn't have this, and they were just in a stall. The pilot flying was confused, and he says, "I do not have control of the airplane anymore." 2 seconds later, he says, "I do not have control of the airplane at all." The guy in the left seat, the other co-pilot, responded by saying, "Controls to the left." He was taking over controls. And he pushed his side stick forward to lower the nose, which is what he should have done, obviously, and recover from the stall. However, the guy in the right seat was still pulling full stick back, and the inputs canceled each other out. And this is, it's mentioned in the accident report. They don't really say, hey, the fact that the sticks weren't coupled, they didn't know that they were both putting in opposite commands. If they could have felt the other guy on there, they would have known. Airbus also, of course, has dual input, but when you got stall warning and all this other stuff going off, a lot of commands, a lot of enunciations, it can get very confusing. Yeah, there is a dual input thing, but it can be lost in the fog of war, if you will. The other thing Airbus developed, and I thought it was kind of nice, is on the top of the stick there, they were putting a little stick shaker, which kind of indicated that two people were putting stick inputs, and evaluated that. And I actually thought that was pretty good, but they didn't have it, and I don't think it's been readily installed. Well, they summoned the captain back to the cockpit, of course, and the aircraft was in a stall. It was descending. There came a point where the co-pilot in the right seat again reduced the pitch, but there's an interesting aspect here. If the AOA is too far out of limits, it takes the stall warning away because it thinks it's invalid. So when he reduced the pitch, the AOA came back into what was considered a normal range, and they got the stall indication. Now, okay, you're trying to recover from a stall. You have no stall indication because it had stopped. Now you're trying to recover, and it tells you you're stalling again. Well, talk about confusion. So he pulled the stick back, and the angle attack now increased up to 35 degrees, and that's where it maintained itself all the way to the impact. The one co-pilot responded, "We've lost all control of the airplane. We do not understand anything. We have tried everything." Well, they thought they had tried everything because they reduced pitch, but it still indicated a stall. Just shortly before they were to impact, the captain realized that they were holding full aft stick, and he because they were in the stall, they were trying to climb instead of reducing the stall. But the captain says, "No, don't climb. No." But by that time, when he instructed them to reduce pitch, it was just too late. The co-pilot, without informing anybody, the co-pilot on the right, without informing anybody, still was holding his stick all the way back. So at most, on the other side, what you can do, unless you hit the override button, where you take control of it, is they sum, and you just have essentially no input. Now here's the stick, and you see that little depression on the top of it? That's where they put that's where they mounted the vibrator, at least for our test condition. That little red button is where you can take priority, and they teach you, at least my airline, if you're going to take control, and you're taking control, you hit the priority left or the priority right. Now, if it's a simple just transfer of control, you're flying, that's fine. But if there's a little more egregious situation where you want to have absolute positive control, you take that, you'll get a little arrow saying, priority left, priority right, and all that sort of stuff. But nobody ever did that to take full control. Now, if you do that, it locks the other guy's stick out. So it doesn't matter what he's doing. You've taken control. But they didn't do that. And unfortunately, 3 hours and 45 minutes after takeoff, they hit the water at 107 knots. They were descending at 10,000 feet per minute, and the aircraft remained stalled almost the entire descent from 38,000 feet. Now, the interesting thing, of course, you're out over the Atlantic. You're not in direct contact with anybody as such, and the aircraft just essentially disappeared. There was no, mayday call, no response to everybody. They were missing check-ins, so they started basically a communication search. Now, of course, the interesting thing is you have ACARs on these airplanes, as you probably know. Anybody familiar with the Malaysian Airlines disappearance know that they have the ACAR system, which is Aircraft Communications Addressing and Reporting System, and this is sending out information on the aircraft status. So the people on the ground were able to determine the status of the airplane and later realize, kind of what's going on here, and piece things together at the end. The interesting thing about this is, this system is great because I was flying a 777. We were going Chicago to Europe somewhere, and I get a call from the maintenance people who says, we've been watching your oil quantity there. It's decreasing. It's still okay, but you may want to keep an eye on that engine. And the funny thing was, I hadn't even noticed it yet, and they were calling me to tell me, the situation. Now, one thing I'd like to point out is there is a procedure for airspeed Mach unreliable, and this is an emergency procedure, and it basically says, the system will disconnect itself, but it says, just to ensure, disengage the autopilot, disengage the auto throttles, turn the flight directors off because they can just be confusing, and then altitude and thrust adjust. And that refers you, okay, that's the immediate action, QRC, quick reference checklist. Then it takes you to the reference action, and basically it says, hey, this is where you are, this is where you put the nose, and play with the power, and this is basically what it'll give you. And if they would have done that, there would not have been people hauling pieces of the aircraft out of the ocean. Now, a lot of things came out in the final report. They're talking about inconsistencies of the airspeed, Clue's lack of practical training in manually handling the aircraft, both at high altitude and events of abnormality of airspeed indication. The cockpit's lack of a clear display of the inconsistencies in airspeed readings identified by the flight computers. So it wasn't really terribly obvious that they had not a good situation, and they faulted the crew's lack of response to the stall warning, whether due to a failure to identify the oral warnings, to the transient of the stall warnings that could have been considered spurious. And one of the things about this was, you can get high-speed buffet and you can get low-speed buffet. And, of course, people who have flown the U-2 know that those can be 2 knots apart at times. You can actually, in a turn, have the outside wing in Mach buffet and the inside wing in stall buffet. But, as usual, I digress. But anyway, part of this whole thing was it was very confusing. And they had a lot of alarms going off in the cockpit. There was a lot of confusion. And when the AOA system went to extreme values, it just dropped out of the whole picture and said, hey, we don't know what's going on. You got it. And, of course, that's when the pitch and the power should have helped him out in this. But basically, it was a lack of basic flying ability, but you know, a lot of times this airplane is touted as being very sophisticated and keeping the pilots out of trouble. And sometimes, you know, one of the worst things you can do is be overconfident in the ability of the system to protect you. So that's my take on this accident. I hope you found it interesting, informative. Thanks for watching.